So today we're going to move into chapter 8. Be quiet. We're going to move into chapter 8, and we're talking about sampling distributions. So far, we've been talking about discrete and continuous distributions, and they were just one thing. Okay. This chapter, we're moving on to sampling distributions, and it is what the name sounds like it is. It is a distribution of a sample. So not just one thing, like not just an X, not just a percentage, it is a sampling, a distribution of a sample. So we're going to discover today, we're going to work to discover the most important theorem in inferential statistics. So I'm going to give two people a die. So you guys are a team, right? You and Randall are a team. Let's see, two people are sitting close together. You two are a team. You two are a team. Oh, I need another one. You want to sit there? Two more teams, I need. Okay. So here's what we're going to do, okay? We are going to take some samples of some dye. And what I would like you to do is, every team has two people. One person is going to have a laptop out there, going to be the recorder, and the other person is going to be my die roller, okay? So if you can handle that task, okay? So the recorder, I want you to go to chapter 8 in Blackboard, and under chapter 8, I want you to click on Dice Experiment Google Docs. So Dice Experiment Google Docs. And when you click on that, a Google Doc spreadsheet will open up. Okay, a Google Doc spreadsheet will open up. You guys with me? Okay. One of the tabs on that spreadsheet says 11 o'clock class, and there are 8 columns to represent the 8 teams. So who's a team? Put your hand up if you're a team. So you're team 1, team 2, team 3, team 4, 5, 6, 7, and 8, okay? So you'll only enter into your column, right? So what I want you to do is roll that die 30 times and record the results. You know what I'm saying? You guys got it? Go. What's that? You got to go to 11 o'clock class tab. Yeah, don't clear anything out. Go to 11 o'clock class tab. So team 7's all over it already. They're ahead of the game. Team 2. Hey, what's team 8 doing? Hey, who's team 8? What's that? What is your user ID?
3-1.
No, like your email user ID.
LXB.
LD. LXB.
107.
Okay, you should be in now. You got to probably refresh. Anonymous dinosaur, I like that name. All right, looks like we're getting our sample. Team 4, laggards. We almost, who's team 4?
Right here.
All right, come on, Randall.
Yeah, it's not that.
All right, we're close to done. All right, so before we analyze this, let's think about what our analysis is going to show. Okay, so I'm going to graph this. I'm going to figure out a mean. I'll figure out a standard deviation. But before I graph it, I want you to tell me what it might look like. So this is a distribution. What are the possibilities of this distribution? I think we can figure that out. What are the possibilities of this distribution? Come on, what are the possibilities? 1 through 6, right? So if we look at that, I try to graph this thing. We have 1, 2, 3, 4, 5, and 6. And what do you think shape that should take on? If we graph the number of 1s we get, the number of 2s, the number of 3s, the number of 4s, the number of 5s, the number of 6. What shape should that take on? Bell shaped? So you think we're going to get more 3s and 4s than we'll get 1s and 6s? Yeah, I like that better. So I think, it's going to be kind of uniform, right? It's going to be, we should get the same number of 1s as we get 2s, as we get 3s, 4s, 5s, and 6s. So, and it's not going to be perfect, right? Because what do we sample? 240 times. It's unlikely we got 41s and 42s and 43s, but around there, right? Because eventually that's going to happen if it's a fair die. What do you think about the average? What do you think about the average? What is the average rule going to be? So think about it. It's uniform, symmetrical. Where is an average, a mean, when we think about something that's symmetrical? Where's the mean, the average? It's going to be where? In the middle. So what's in the middle here? Go ahead. 3 and 4, so there you go. That is going to be my average, 3.5, okay? So I think you guys are right. Let's do the analysis, and obviously to do the analysis, I'm going to thank you guys for doing this. I'm going to go to File, Download, Microsoft Excel. I'm going to bring this into Excel. And I'm going to try to put everything in one column, right? This is, 11 o'clock class. Here's the data you guys gathered. So I'm going to open up my clipboard here. And I'm going to take the die 2 column, and I'm going to Control-C that. The 3 column, Control-C that. 4, I think you guys shorted me 1 and 4, group 4, but that's all right. Control-C that. Control-C. 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 And Control-C. And then I'm going to paste all those values, because I just want it in one big column. So I'm going to paste all into that column. I think I have them all, and maybe not. I think I maybe have 240. I don't know. It looks like I got some bonus ones in there. It looks like, I don't know. But anyways, I'm going to analyze. Oops, I got some blanks. Maybe that's why. So get rid of those blanks. I'm going to first try to graph this, and I'm going to do it kind of a quick way. I'm going to do data analysis, and I'm going to kind of do the histogram tool. It's not going to be perfect, but I'm going to use that tool. I'm going to click OK. The input range is B1 down to B. Looks like I got a blank there. Hopefully that doesn't hurt me. B241. I'm going to click labels, chart output, and we'll see what that looks like. And I don't have it beautiful, but you can see pretty much there's the 1s, 2s, 3s, 4s, 5s, 6. And it's not perfectly equal because I only sampled 240, right? But it would be, if I sampled thousands, it would be perfectly equal. Yes. Okay, so let's figure out the average. Okay, and I think you guys told me, or Sean told me specifically, that we think the average will be 3.5. So I'll tell you what I'm going to do. I'm going to do data analysis, descriptive statistics, and I'm going to take that column B once again, and this time I'm going to figure out, all the summary statistics. And it comes out and it tells me the average that I got is the true average was 3.65, which was close. And the reason for that is we only sampled 240. I also want to look at the variance. The variance, which, as you guys know, measures the spread, how spread out things are, is 2.72. So I'm going to put that here as well. That variance is equal to 2.72. Okay, so that's the first experiment that I want to do. The second experiment, I need you guys to partner up. So where's team 1 and 2? Okay, you guys are partners now. 3 and 4? Oh no, you're going to have to come up. These guys need some help, so you guys will help. 3 and 4. 5 and 6? Okay, 5 and 6, you guys are partners. And 7 and 8, you guys back row, right? You're partners. Okay? What I want to do this time is something a little bit differently. Let's go to the document. What I want you to do is I want you to each roll, but then I want you to add your die together. So if the first roll, die 1 gets a 3, 1 gets a 5, that's an 8, right? So you're going to do, you guys can't see this, but there's a tab that says die 1, and it says 11 o'clock, 2 die sum. So all I want you to do is add them together, right? So if you roll a 1 and a 1, that's a 2. If you roll a 1 and a 6, that's a 7. And put that in there. So you got to work together. So you're going to have a reporter and 2 rollers now. And you have to add them together. Does this make sense? Yes? You guys know what we're doing? Only one person got to record it? Yeah, only one person's got to record it. 2 people have to roll. We need 3 people. Huh?
I had 6
Hey, what's team 3 and 4 doing? Where are you guys going? Why you put it on paper first? Oh, all right, come on. We're electronic era.
9, 5, 8,
You guys do this better than us. Oh, no way, you
All right, we're getting our data. $98, no. All right, we're almost done. All right, this time we're going to bring this into Excel. But I don't really care about the sum. What I really want is the average. But I thought we'd make Excel do the average. But you guys can do the sum, right? You can add 1 and 5, but then dividing by 2. I'm like, oh, well, I don't want to eat my throat. So we'll make Excel do that. But what I really want to look at is we're rolling 2 die, and I'm going to average them together. That's kind of like a sampling distribution, right? We took a sample of 2 and averaged them together. So the first one was just plain, right? It was just a sample. This is a sampling distribution. We're taking 2 and averaging them together. So we got all our data. So I'm going to download this into Excel once again. Let's go to 11 o'clock sum. And let's go to the clipboard here. And I'm going to copy, copy, and copy. And then I'm going to paste it all into the bottom of this one. Now, before I graph it, I want you guys to think about, help me figure out what it's going to look like before I graph this. Just because you could probably think about it. What's the spread of the observations? You know, oh, I'm sorry. Let's do this first. So I have this column. Let me clear the clipboard. And what I'm going to do is I'm going to put a column next to it, and I figure out the average. Let's do that first. So I'm going to say, if I rolled a combination of a 6, what's the average roll of that deal? 3. So how did you do that? Divided by 2, right? So you'd agree if I rolled a 10, that was an average of 5. Oh, did I do the wrong column? Did I not paste all? What's going on? Did I forget to paste? I forgot to paste. All right, let me redo this. Struggling. Copy. 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 Paste all. So if we average it, we would take the sum, which you guys figured out for me, divided by 2. So if we rolled a total of 6, that was an average roll of 3. Go the whole way down here. You know, if we rolled a 9, that was an average of 4.5. Rolled an 8, that's an average of 4. So that column represents my average of the 2 rolls. Does that make sense? Okay, so we're going to have half as many observations, but we average them together. I want to graph this and figure out the average of this. So before I graph it, though, I want you guys to think about what that's going to look like. What's the spread of that average? Did you guys notice what the smallest thing was and what the largest thing was? What's the highest value I can average and what's the lowest value I can average? What's the lowest thing I can average to? 1, right? A roll of 1 and 1 and averages to 1. What's the highest thing I can average to? All right, so it's still spread from 1 to 6, right? If I roll a 6 and a 6. How about the observations? Where are most of the observations and where are there fewer observations? How do I get an average of 1? There's only one way to get an average of 1. What is that way? Roll a 2, right? And there's only, what? 1 and a 1. Okay. How about a roll 6? There's only one way to get that. Roll a 6 and a 6 average, right? How about getting an average of 4? How many ways can I get an average of 4? 2 and 6. I'm sorry, no. Yeah, 2 and 6. What?
3 and 5.
3 and 5. 4 and 4. Right? More ways. Yes. How can I get an average of 3.5? At total 7. So what? 1 and a 6. 5 and 2. 3 and 4. Right? So what are we saying? Very few out here and more toward the middle. So think about an observation that we know that has very few on the outside, but a lot in the middle. The most famous observation of them all. What's that? Yeah, I think so, right? And what do you think about the middle? What do you think about the middle? What's going to be the average? What's going to be the average? We said this average was going to be about 3.5. What do you think the average of this one's going to be? Yeah, it's going to be the same. So I know it's not going to be perfect, but it's still going to be 3.5. Let's figure that out. Let's graph it, and then we'll figure out the average of the average, right? So I'm going to go into Excel. I'm going to go data analysis, histogram once again. Input range is C1 through C121. I'm not going to give it a bin range. I'm going to make it do that itself. I click OK. And even though it's not perfect, okay, we can kind of see it's bell-shaped. We only sampled, 120, but we can kind of see this looks pretty good over here. Not too many here. I don't know why we have a 0, but it looks pretty good here, not so good there. But it's kind of bell-shaped. Let's go back to that, and let's do data analysis, descriptive statistics, and let's take that average column, that's column C, and let's figure out summary statistics for that. And you see our average still comes out to be about 3.5. It's actually, we said it was going to be 3.5, but it was 3.53. And the variance is 1.67. Okay, the variance is 1.67. So if we take a look at it, a couple things happened, right? When we did one die, it was what? Not normally shaped. It was kind of uniformly shaped. The average was 3.5. The variance was 2.72. When I did two die, the average came out to be still around 3.5. And the variance went from 2.72 to 1.67. Now, we only have so much time in this class. So what I want to do is, let's go a little further. Let's do 3 die and 4 die and 5 die, and maybe 25 die. Crazy, right? But I don't have 25 die, but what I do have is I have a simulator. So go to Blackboard, go to material by chapter, go to chapter 8, and under chapter 8, you see something says dice roll applet, little applet thing. Click on that. Okay, under chapter 8 it says dice roll applet. And I want you to click on that. And a couple things I want you to do. I want you to uncheck show distribution because we'll figure that out ourselves. We don't need it to show it to us. And we're going to use a fair die. And instead of sum of scores, change it to average score. Average score. And let's just do, I know we did it ourselves, but we only did, 240 rolls. This can do a lot more rolls. So let's just do one die. Okay, and I'm just going to roll it once. I'm going to say, all right, I rolled a 1. That has an average of 1. I roll a 2. That has an average of 2. And it starts to graph it. You guys see this? And I just rolled a 5. Boom, boom, boom. But you know what? I'm going to roll this damn thing 1,000 times. So I'm going to go to stop 10 and change it to a stop 1,000. And then I'm going to hit the fast forward button. And it's going to simulate 1,000 rolls of that die. And what starts happening, if we look at this thing, the more and more I roll, the more it kind of flattens out and takes the shape that I expected the shape to take, that flatness, if you will. I'm going to roll 850, roll 900. That looks pretty good. If I roll another 1,000, it's going to even get better, right? Because it's going to eventually take on that shape. If I rolled a million billion times, it would eventually take on that shape. So now I'm going to roll 1,500. I'm going to roll 1,600. And it kind of proves what we thought and what our little experiment showed. Let's go to 2 die. So the little slider, you see where it says n is equal to 1? Slide that over, so now we're going to roll 2 die. Let's just roll 2 die once. All right, we got a 4 and a 5. And that averaged to a 4 and a 6, I'm sorry, that averaged to a 5, and we graphed it. Roll again, a 2 and a 1, that averaged 1.5. Let's quit screwing around. Let's go 1,000 times. Rolling 2 die, averaging them together 1,000 times. Wow, we can definitely start seeing, our shape wasn't great, but that's because I only did it 120 times. We're at 600 now. We're at 700 now. We can definitely start to see that shape come on. But a couple of things we know is that mean is still the same, is it not? Mean still the middle. How about, what do we say about the standard deviation or the variance, how the spread of it? When we did 2 die, are there more values near the mean or more values away from the mean? When we do 2 die, are there more values toward the mean or more values away from the mean? There's more toward the mean, which means lower standard deviation, and that's what we saw, right? The standard deviation with 1 die, we calculated out, went from 2.72 to 1.67. We didn't do this with the physical die, but let's go Yahtzee style. Let's go up to 5. Isn't there 5 die in Yahtzee? You guys ever play Yahtzee? No? It's a good game. They have like a plastic cup and you shake the die in it. That's a good feeling just to shake those die. Something good about that. So let's roll 5 die once. 6, 2, 6, 1, 2. That sums to 17. That's an average of 3.4. Let's roll them again. 3, 2, 4, 5, 5. That's an average of 3.8. Let's go big. Let's roll that damn thing 1,000 times. 5 die 1,000 times and average them together. Going. We want processing power here. A couple things we note. What shape is this still? Still bell shaped. What do you think about the mean? Still 3.5, right? Still in the middle. How about on the extremes? Are there less values out there or more values? Less, because to get an average of 1, I have to roll 5, 1. That's Yahtzee. That's hard to get, right? That's 1/6 to the 5th power, which is unlikely. Let's go big, big, big. Let's go to, what's this slider take us out to? Let's roll 25 die. That would be fun to do that, yes? Let's roll them once. Boom. And we get a 1, a 6. I'm not going to go through them. But we add those 25 up, divide by 25, we get an average of 3.4. Let's do it again. Boom. We get an average of 3.08. Let's go crazy. And we'll roll those die. 25 die 1,000 times. And a couple things that we see. Okay? What shape is that taking on? Still bell shaped, right? Where's the mean at? Still the middle. Very good. How about the standard deviation variance? Are there any 1s? Hell, there's no 1s. There's no 6s. Hell, there's not a 2 average. There's not a 4 average. Everything, almost everything is around the mean, right? Yeah. So think about what we've learned. There's a couple things that we learned. And what we just kind of figured out on our own is what is called the foundational theorem of inferential statistics, and it's called the central limit theorem, or CLT for short, right? And there's only 3 parts to that thing. The glare there. There's only 3 parts. The first one is when we sample 2 die or 25 die or 5 die, the mean didn't change, right? So the first part is the mean of the sampling distribution, and that's what this means, the average of the averages, right? The averages of the averages of the sampling distribution was equal to the original average. It didn't change, right? Went from 3.5, doesn't matter how many, it stayed 3.5. Didn't change. I'm going to skip down to the third thing. It's easier. The third thing is when I sampled enough for a sampling distribution, what shape did they all take on? 2 die, 3 die, 5 die, 25 die. Bell shape, very good. Normal shaped. And the second thing, let's talk about the variance. What happened to the variance of the sampling distribution? Just what direction did it go? The more I sampled, did it get smaller or bigger? The more I sampled, smaller it got. And in fact, what the central limit theorem says is the variance of the sampling distribution is equal to the original variance divided by n, where n is the amount I sample. Like, it should go down, if I sample 2 die, it goes down by half. If I sample 3 die, it goes by a third. If I sample 25 die, it's 1/25th of what it was. Does that make sense? That's variance. What's the relationship between variance and standard deviation? You guys remember? Standard deviation is the square root of variance, right? So if I take the square root of both sides, I get the standard deviation of the sampling distribution is equal to original standard deviation divided by the square root of n. Now, that is what I have on the board, and I'm going to put it up in, ooh, I almost fell there. What I'm going to put on Blackboard here in a second, if I can find it, is the central limit theorem. Now, this is the more proper, I guess, statement of it. Oops, pull up the wrong slides. The central limit theorem says this: the mean of the sampling distribution is equal to the original mean. The variance is equal to original variance divided by n. And it also says if the original distribution wasn't normal, if I sample enough, the sampling distribution will become normal, bell-shaped, which is great for us because I know everything there is to know about the distribution. These are good things for us. And I want you to think about why this is the foundational theorem of statistical inference. Let's say this. Let's throw out this. Let's say that Career Services at St. Francis University has made this claim. They have said that the average number of job offers that a business student graduating gets is 10 with a standard deviation of 3 job offers. That's what they said. You get 10 job offers, standard deviation of 3. That's what their claim is, right? How would you try to investigate that claim? What would you do to try and investigate that claim? What would you say? You say, all right, thanks, take it for what it's worth. But I've tasked you, I'm your boss, I said, investigate that claim. What would you do? Okay. You sample, yeah. So you go, you ask a buddy that graduated from business, and he said, no, I got 1 job offer. So what do you think? You're thinking at this point, like, that claim doesn't seem quite right. But are you willing to call Career Services liars at this point? You only sampled 1 dude, right? So what might you do, Evan? Sample more, right? And what does this tell us? The more I sample, there's some value out there that's the true average, right? The true average. And the more I sample, what happens with that sample distribution? What is it doing? The more I sample, what is it doing? It's zeroing in on that true value, right? Which is very powerful and does it pretty damn quickly. We sampled 25, it was like, right? It was like very zeroed in. That's why, if you've ever seen like estimations for, how many people watched this show last night or what Barack Obama's approval rating is, they don't talk to every damn woman, child in the United States. They do a sample and they're pretty confident because they zoomed right in on it, right? That's what sampling distribution does, okay? So how are we going to use this? Well, let me make another example. Okay, let me make another example. Let's say this. Let's say, once again, it's a claim. Let's say, make it simple. Let's say, yeah, we'll use that same example. Let's say someone has told me the average number of job offers St. Francis grads get is 10, and we'll say with a standard deviation of 2 job offers. Okay? Look at that. It's like a glare. How do I get rid of that? I want to know, okay, if this is true, what's the probability that I sample someone, just one person, X, we're talking about X, and they got less than, I don't know, let's say 7 job offers. What's the probability that, let's do 8 job offers. What's the odds that they got less than 8 job offers? Now this isn't new to us. Okay, this isn't new to us. What's the odds that if I sample one dude, he got less than 8 job offers? How would I figure that out? What would I have to do? This is a continuous probability distribution. To find that, I want to find the area under the curve. I would end with a Z lookup, right? But what would area under the curve is equal to that probability, right? So what do I need to do with that X value? Convert it to a Z value. And this is the formula I use to do that. Z is equal to X minus the mean divided by the standard deviation. You guys recall? Let's do it. The probability that X is less than A is the same as the probability Z is less than 8 minus 10 divided by 2. It's the probability Z is less than negative 1.0. Well, I'm going to have to use my trusty Z table. Negative 1.0 gives me 1.1587. So there's like a 16% chance that happens. So I did that. I sampled one person. They had less than 8 offers. 16% chance happens, right? It happens. What if I sample 4 people and I average them together and they average less than 8 job offers? What's the odds of that happening? So I'm no longer talking about one person with less than 8 job offers. I'm talking about averaging together 4 and their average being less than 8. Okay? Not just one person, but their average being less than 8. Well, let's think about what the central limit theorem tells me. We're not talking about X anymore, we're talking about X bar. What happens when we talk about X bar? What happens to the mean of this thing? What happens to the mean? What did it say happens with the mean? The mean stays the same. What happens with the standard deviations? Go up or down? Goes down. So visually, let's draw that. And this isn't to scale or anything, but it becomes narrower and more peaked. So the probability that X bar is less than 8 looks like it's going to be smaller, doesn't it? Let's figure that out. I have a formula that converts X's to Z's. I need a formula to convert X bars to Z's. Well, let's make this formula that formula. Well, let's just put it X bar because we're looking for X bar. What do we say about the mean? What happens, part 1 of the central limit theorem, what about the mean? It does what? The mean, good, I don't have to deal with that. What about the standard deviation? The standard deviation is equal to the original standard deviation divided by square root of n. That's my new formula. That's it. This formula now that the central limit theorem has given me converts X bars to Z's. Not just X's to Z's, but this is the formula I want to use to convert X bars to Z's. So let's do it. The probability that Z is less than 8 minus 10, because the mean's still 10. Standard deviation's 2. Hey, but I sampled 4. So the square root of 4, that gives me the probability Z is less than, that's negative 2. 2 divided by the square root of 4 is 2 by 1. The probability Z is less than negative 2.0. Let's look up negative 2.0. Negative 2.0 gives me 0.0228. And as I thought about it, and I was right, it's smaller, right? The odds that I sampled 4 people and they had less than 8 job offers goes down even more. It goes down to 2%, but it could happen. I'm not going to go call career services a liar at this point because it happens, right? It could happen. That could be true and that could happen. But let's say I go big. And let's say I sample 100 graduates. And I want to know the probability that those 100 graduates, I average together all their job offers, What's the odds that that comes out to be less than 8? So tell me what happens to the new distribution. I sample 100 now. So what happens to it? The mean does what? Stays the same. Standard deviation goes down even more, so it's even more tightly wrapped around the 10. And just visually looking at it, I know it's an awful drawing, but what part of that new curve that I drew is less than 8? Because I just drew it like here and here. Virtually 0. Let's figure it out mathematically. Well, the probability that z is less than 8 minus 10, standard deviation is 2 divided by the square root of 100. Doing the math quickly in my head, that gives me the probability z is less than negative 10. Wow, I know our curve goes from negative 3.89 to positive 3.89, most of it anyways. So the odds that it's less than negative 10 is what? What? Virtually 0, okay? So virtually 0. So what? So let's say I did this. Let's say I actually went out and took a sample of 100 St. Francis graduates, and I averaged together, they had 7.5 job offers, which is less than 8. So we're saying mathematically that if this is the case, this should never happen. Virtually 0 chance of that happening, right? I just went out and sampled 100, and it happened. I got an average less than 7.5. What does that mean? What does that mean? What does that mean? A bloody miracle? What does that mean? This happens all the time. What does it make you think? You just go, oh, okay. You're saying 10. I sampled 100, got an average of 7.8. Mathematically, that should never happen, but it just did. We just happen to find the worst people randomly. So what do you think? Very good. The original claim is wrong, right? We do this all the time in the world of business. If you think about it, some of you guys are going to be auditors, right? So what does an auditor do? What does an auditor do? Checks people, right? Checks things. So you go into a business, they say, hey, this is our deal, and you can't trust them, so you sample, and you figure out, and you say, hey, based on our sample, what you're telling us is not true, right? So we think there's something up here, right? Now this is a goofy example, I know, but you guys pump your own gas. If you're not from New Jersey, you pump your own gas, right? So if you ever looked at the side of the pump, because I have a compulsion, I like read every damn thing. But anyways, look at the side of the pump. It has like the Pennsylvania Department of Weights and Measures, and has a little calendar on it, and has like January, a hole punch for January. You ever see that? So what does that indicate? Someone is inspecting those pumps, right? And what are they doing? Do you think, because they're making sure they're accurate. Like if you pay for a gallon of gas, the price is right, you get a gallon of gas. What do you think they do? I've never seen this happen, so I might be making this shit up, but what do you think happens? What do you think happens for the sampling? Like before them to punch that thing and say, yeah, you're good. What do you think they do? I don't know. You think they just say, oh, you're good, your sheets. What'd you do? Yes?
I feel like a gallon bucket and fill up and see if it matches up.
It's a sample, right? You'd say like, all right, I'm gonna sample maybe a 5-gallon bucket, right? Average of 5 gallons, and hey, all right, it's filled exactly. Maybe I weighed the damn thing, it's very precise. The cost is 5, I sample, right? That's what we do, right? Sample, and then we make an inference like, hey, this sample came out wrong, so we're making an inference that your pumps, you're cheating people, right? Whatever it might be. That's what statistical inference is all about, right? You take a sample to understand the whole, yes? And what's great about the central limit theorem is it shows you, that theorem says, hey, if we sample, it really, really zeroes in. You can come out and say, Barack Obama's approval rating right now is 48% plus or minus 2%. Like, how can you be so sure? Well, because I sampled 500 people randomly. I didn't sample, they didn't talk to Miko, they didn't talk to you guys, but hey, boom, we know statistically, we sampled 500, we're zeroing in on its true population, its true popularity rating, right? And we're not perfect. That's why you see plus or minus 2%, right? It's not perfect. We don't say, hey, we know it for sure. We say plus or minus 2% because we know, hey, we've zeroed in, but there's still some room for error. Yes? That's what statistical inference is all about. And the central limit theorem is the theorem that says this is why it's possible and this is why it's powerful. Here's what I want you guys to do. So that's a long road to get here because the math is pretty easy, but I think it's really worth spending that much time getting there because it's that important to the world of statistical inference. In your book, I want to let you look at like number 7. I want you to do number 7. And talking about North American women. The heights of North American women are normally distributed with a mean of 64 inches and a standard deviation of 2 inches. Okay, that's the height of North American women. I guess Canadian and United States women. That's all North America, right? 5'4" with a standard deviation of 2 inches. So, A, B, and C I want you to do. What is the probability that A, randomly selected woman, one woman, I'm not talking about X bar, not an average of women's height, but one woman is taller than 66 inches. B, we're saying let's take 4 women, average their height together. What's the odds that it is greater than 66 inches? And then C, we're saying let's sample 100 women and see what the odds that their height is greater than 100 inches. No, because just one, so it's just X, not X bar. Even if you use the X bar formula though, it's still work. It's because the square root of 1 is 1, right? So, yes, you're right, it's just X, not X bar. So for part A, we just use Z is equal to X minus the mean divided by standard deviation. For B and C, same formula, except square root of N. That church. That's the business. It was a delegate t-shirt there. Yes. Remember delegate? Must have been hell with delegate. You got hand out t-shirt. Central Leland Theorem class of 2017. Throw your names on the back. Yeah. Normal curve on the front.
Yeah, I like that.
Yeah, you got that. Maybe normal curve and put like E in the after outlier.
Now we're really pushing.
4 standard deviations above normal. You may not use a lot of statistics in English, but use the normal curve in conversation. Even if it's not mathematical, throw that in. You ever hear my theory on parenting? Here's my theory on parenting. See if you believe this. So your children, are what they are, right? This is your child born, right? Now they're here, whatever that is. As a parent, I think you can parent them well. Make them a little bit better, right? Give them a good environment. Make them better. So you can probably influence their happiness, their life, probably a standard deviation to the right. Right? Better. What do you think you can do this way? You think a little bit worse or a lot worse? Yeah. You know what I'm saying? I think parenting, you can make children's life a little bit better or a whole lot worse. Does that make sense?
Yeah, definitely.
Yeah. You're talking about that's my theory.
You can make it better or worse.
You can make them a little better, like a standard deviation better, or you can make them 7 standard deviations, ruin their damn life, right? You know what I'm saying? Make them a basket case for life.
Yeah.
You know what I'm saying?
I do.
You know people like that?
Yeah, those people.
Yeah.
Daddy wasn't there.
If you're using dating, Sean, you can say that girl is 3 standard deviations out of my league.
Yeah, that's
Yeah,
that's
you
probably
know?
how I'll say it. Excuse me, man.
I know you're out of my league by at least 4 standard deviations.
I know you're a couple standards.
And the odds of that happening is less than 1%, but would you date me?
I'll take a swing at it now. I don't think she would reject me if I say something like that.
No, I wouldn't.
How many standard deviations about me?
All right, so we're saying North American adult women, 64 inches, standard deviation is 2 inches. And the first part just asks us, hey, what's the probability that 1, we're talking about x, is greater than 66 inches? Well, here's the formula to convert x's to z's. So the probability that z is greater than 66 minus 64 divided by 2 gives me the probability z is greater than 1.0. It's greater than, so it's 1 minus, if I look up 1.0, I get 0.8413, and I get roughly 16%. Make sense? Part B, though, says, hey, if I sample 4 women, what's the odds that their average height is greater than 66? So I'm not talking about x anymore. I'm talking about x bar. So the formula to convert x bars to z's looks like this. X bar minus the mean divided by the standard deviation divided by the square root of n. Do it, 66 minus 64, 2 square root of 4. Gives me the probability z is greater than 2.0. Should have done this. This is part 1. And that's the odds, 15.87. But if we sample 4, the central limit theorem tells me, hey, it gets tighter around the mean. Now it might be only a little bit. If we look at 2.0, it's 0.9772, so 1 minus 0.9772 is 0.0228. And then finally, even before I do the math, if I sample 100 women and I average them together, what the central limit, that's like the 25 die one, right? Central limit theorem tells me, hey, that thing's going to get real tight around the true mean. So what's the odds? What's the odds that it's greater than 66? Just looking at it. Yeah, let's figure it out though. N is equal to 100. probability x bar is greater than 66. You guys can't see this. Is the probability z is greater than 66 minus 64. 2 divided by the square root of 100 gives me the probability z is greater than 10.0. Remember the normal curve, about negative 3.89 here, positive 3.89 here. What part of the curve is greater than 10.0, the z curve? Yeah, virtually 0, right? So, say I sample 100 women, I average their height together, and it comes out to be 66.5 inches. What does that make me think? There's only two ways that can happen. A, I happen to sample the tallest women. Maybe I was at, like a basketball clinic or something like that. So that wasn't a good sample. That was a bad, biased sample. Or what? Or what? Shouldn't happen, and it just happened. So what does that make me think? Something was wrong with the array. So think about examples of this. Quality control, like you're trying to produce something with certain specifications. But you can't look at every damn thing you produce, so you sample. And you measure that sample. You say, based on this sample, we're making an inference that something's wrong with our production line. Yes? This is what the central limit theorem allows me to do. The CLT. Here is what I'd like you to do for homework. In syllabus week.
Whoa.
Syllabus week. It's day.
No, that's so sweet.
Syllabus day. So we did 7, right? We just did 7. So I want you to do 9, 11, and 15. They're on pages 130 and 31 of your text. And they're the same. They're the same thing we just did. Same basic.
Yes, I say 9, 11,
9, 11, and 15. Oh, 15. Page 130, 131. 9, 11, 15. Have a very nice first weekend. Be safe. Yeah, don't ruin your semester weekend 1.
got that right.